So welcome back, everyone. It's my great pleasure to introduce Martina Juhnke from the Universität Osnabrück. She will give lectures on symmetries in algebra and combinatorics in the finite and infinite settings, together with Uwe Nagel from the University of Kentucky. And their TA is Aida Marai. Correct me if I'm mispronouncing.
Great job.
Oh, okay, good. And yeah, so if you have any questions, as Alessio said, feel free to interrupt. Otherwise, you can wait the anonymous and non-recorded QA session at the end of the lecture. Martina, stage is yours.
Okay, thanks. So first of all, thanks to the organizers for organizing this nice workshop. I guess it's a really nice opportunity for everybody who can participate in it. So Lorenzo already said that Uwe and I will be speaking about symmetries in algebra and combinatorics. So my part is mainly combinatorics. Also, we will speak about symmetries in finite and infinite settings. Again, my part will be finite settings. So Uwe will mostly stick to the infinite case, or yeah, he will always stick to the infinite case, to be honest. Yeah, and Aida is our TA, as Lorenzo already said, and she also will be there during the coffee breaks, and she will also answer questions. Yeah, so thanks also to Aida. So what's the plan for today? So mainly I would like to speak about lower bound theorems for simplicial complexes which care some kind of symmetry. So I will explain, like in the second part of this talk, what kind of symmetry I'm interested in, or yeah. And one of the prototypical examples will be centrally symmetric complexes, but we won't only focus on those. So what's the rough plan? So I would like to start with simplicial complexes and Stanley-Wiesner rings in the first part. And then I will go on and talk about Cohn-Macaulay complexes, which will play a role. And in the last part, I will, as promised, come to lower bounds. And lower bounds both for Cohn-Macaulay complexes and for polytopes, which both are assumed to care some kind of symmetry. Okay, so let's just start with introducing, or maybe rather recalling, what are simplicial complexes and what are Stanley-Wiesner rings. So delta is a simplicial complex on a certain vertex set, delta simplicial complex on V. So what do we want? We want that delta is a collection of subsets of V. That's the first condition. And the second condition is that it should be closed under inclusion. So meaning if F is in delta, G is a subset of F, then we also want that G is an element of delta. So and then there are several notions we need to define for simplicial complexes. So first of all, elements that lie in delta are called faces. So those elements here are faces. And then every face gets a dimension by just saying, okay, what's the dimension of the face? It's just the cardinality of the face minus 1. So we also said dim F just as a cardinality of F minus 1. So for example, if I have a face which just corresponds to one element, then that's just a vertex and it has dimension 0. And that's also how you should imagine if you have what you think it should be the dimension. Similar, if I have a face which contains 2 elements, then it has dimension 1, and you should just think about an edge. Good. So now, if we have the dimension of faces, we can also say what's the dimension of delta, and that's just the maximum of the dimensions of the faces. So in particular, if you look at the definition of a simplicial complex, it's immediate that always, if the simplicial complex is not completely trivial, then you will always have the empty set inside. And the empty set has just cardinality 0, so it's a face of dimension minus 1. This just as a very, very simple example. But now let's look at some more examples. So first of all, let's just start with zero-dimensional complexes. So what are those? Those just consist of points. So you just have a collection of isolated points. So nothing else. So this is not really interesting. So, and you should think about this really as a collection of vertices in this way. So here we have vertices 1 to up to n, let's say. Okay, now a little bit more interesting. What about one-dimensional simplicial complexes? So those are just graphs. So here you have a collection of vertices and a collection of edges. So to give you a precise example, you could have something like this. So for example, let me draw something. So here we have a simplicial complex which has 7 vertices. So we have 1, 2, 3, 4, 5, 6, 7, and we have 7 edges. So, I mean, I didn't define simplicial complexes in a geometric way, but I assume that you have seen this before. So what you basically do is you have the edges. So for example, you have this edge 6, 7. So 6, 7 is an element of the simplicial complex. And since this one is closed under inclusion, we also know that 6 has to lie inside, and we know that the 7 has to lie inside. And this is what this is basically saying. So in general, if you're in higher dimensions, what you get just simplices, and you get all faces of the simplices, which also have to lie inside. So let's look at one more example, maybe. So let's look for maybe 2 more examples, to be honest. So let's first of all take the following complex. Let's take this one. Then we have an edge there, edge there. And then what I want is, I want those 2 triangles, which I've tried to fill. I want to have the edge down here, and I want to have the edge which is above. So here you could write this. Let's maybe just do this. So if I want to write this really as a set system, I would write it as 1, 2, 3, and here I'm just omitting parentheses. So I will do this also later, just to have some kind of shorter notation. I would have the face 1, 4, 5. Then I have the edges 5, 6, 2, 4, and then I have all subsets. So for example, I have 1, 2, which corresponds to this edge from 1 to 2. I have the edge 1, 3, 2, 3, 1, 4, 4, 5, 1, 5. And then I have all the vertices, 1 up to 6. And as always, I have the empty set. And then what about the dimension? In this case, the dimension of the simplicial complex is 2, because I have 2 faces which have cardinality 3. And yeah, that's it. So let's just say dim delta is 2 in this case. So now another example, and this is somehow a very typical example. So if you think about like large classes of simplicial complexes, so where do they appear? So one class is just, for example, triangulations of manifolds. You take your favorite manifold. For example, you can take the torus if you like, and then just take any triangulation of this one. So this will give you a simplicial complex. So I won't be interested, at least not today and not tomorrow, in triangulation of manifolds, but I would like to look at another class. I would like to look at simplicial polytopes. So you had polytopes already in Matt's lecture today, and I guess everybody knows what the polytope is. So if you have a simplicial polytope, then the boundary complex of the simplicial polytope is just a prototype of a simplicial complex. That's nothing else. So let's just look at, let's say, maybe not my favorite, but one of my favorite examples, which you will see several times. That's the following. Let's take the cross polytope. So I'm trying to draw it first in dimension 3. Okay. So if you have the octahedron, so how is it defined? Let's say this is our delta. And you could just say, okay, if I take the unit vectors, then I would take the positives and the negatives of all the unit vectors. And then I would take the convex hull. So convex hull of plus minus E1, E2, E3. So this is how you would define it in a geometric way. That's a cross polytope. So now if you take the boundary complex, what you get is a simplicial complex. And the interesting feature of this simplicial complex is that it's our first example of a simplicial complex with a symmetry. Namely, we have a 2 symmetry here. And I will tell you why 2 when we come to symmetries. But so what does it mean? So basically you have an involution on this complex, which just maps you EI to minus EI. So if you do this operation twice, you just regain your simplicial polytope back. You just regain the cross polytope back. And that's somehow the simplest example of a symmetry. We will come to this later. It's also something which we call centrally symmetric. That's another way of phrasing this. Okay. So are there any questions so far? So I can't see the chat, to be honest. I don't know why. But so Lorenzo, are there any questions?
There is nothing in the chat right now.
Okay, great.
I'll let you know if there's.
Can I ask a quick question?
Sure.
What does it mean when you refer to it as a cross polytope?
Sorry, what does it mean?
When you refer to it as a cross polytope?
You mean why cross polytope?
Where does the cross word come from? Or what is that referring to?
That's a good question. I've never thought about this. I mean, sorry, to be honest, I don't know where the name comes from.
It's a cross product of 3 intervals.
It's a join of intervals.
Yeah, join. Yeah, but it looks like.
Yeah, you could see it maybe this way. Yeah.
So
Yeah.
So in the 2-dimensional case, if you draw it on a plane and if you like represent points as vectors,
it looks like a cross, but it's like
I don't know.
Yeah, maybe. Okay. So what will we be interested in? So I said at the beginning that I would like to speak about phase numbers. So which means that maybe now is the right time to define the phase numbers. So how do we define phase numbers of a simplicial complex? So we just say, okay, if we have a simplicial complex, delta, then I set Fi delta to be the number of phases that have dimension I. And just to recall, so dimension I just meant the cardinality of F minus 1 equals I. So I count how many vertices does my simplicial complex has. I count how many edges do I have, how many 2 faces, and so on. So if we go back to the examples. So for example, if we look at this first example of this of the 0-dimensional complexes. So if we want to write down the F vector, so here I would just say, okay, F, And F is just a vector consisting of all the Fi's. Here I start with F minus 1. Maybe let's just write this. So I would have F minus 1 and I would have F0. So what is F minus 1? F minus 1 counts the number of faces of dimension -1, so cardinality 0. So this is always a 1. And then I count the number of vertices. And here I have n vertices. So I would just get 1n. So if you write it for the simplicial complex down here, let's just write it as f of delta. Then again, I have 1 for the empty set. Then how many vertices do I have? I have 7. And I've also 7 edges. So in this case, I get 177. So the next example we had was this 2-dimensional complex. So here again, 1 for the empty set. Then we have 6 vertices. We have 8 edges. And we have 2 faces of dimension 2. And finally, for the gross polytope, we have, we have 1 for the empty face. We have 6 vertices. How many edges do we have? So we have 4 which contain E2. We have 4 which contain minus E2. And then we have this foregone, which is somehow lying in the equator. So we have 12. And we have 8 faces of dimension 2 lying in the boundary. So we get 1, 6, 12, 8. So in here, let's just write that f of delta is the vector f minus 1, f0 up to the dimension, so f dim delta of delta. And we already said that here we count the vertices for f0, and f1 would count the numbers of edges and so on. So what's the general problem I would like to consider, or what's the problem which has been studied a lot? It's the problem of if I give you a simplicial complex, or let's say I give you a class of simplicial complexes. So for example, just take boundary complex of simplicial polytopes. Can you find upper or lower bounds for the face numbers? That's the basic idea. And you can ask this for a lot of classes. For example, you could start, as I said, with simplicial polytopes, and then you can just say, okay, let's assume that we have condition B in addition, whatever condition B is. So for example, you could just say, okay, I have a certain symmetry on the simplicial polytope. And then let's just look for the face numbers, or let's try to find lower bounds or upper bounds for the face numbers of simplicial polytopes with a certain symmetry. Okay, so problem, find upper or lower bounds for delta for classes of simplicial complexes. So are there any questions so far?
Sorry, do you mean f of delta in the problem?
Yeah, thanks. I mean f of delta. Okay, so now if you have such a question, so how would you should maybe the first thing to ask is now, how can I find those bounds? So what are tools which are used? And there's like maybe the, I would say the main tool which is used are Stanley-Wiesner rings, which was the second keyword in the title of this first part. Okay, so let's assume again that delta is a simplicial complex. So I won't write this down, but I would just say delta has vertex set, just to make it easier, 1 up to n. So here, n in brackets is 1, 2, up to n. So now, first of all, I define a certain ideal. which I call I delta. So that's the ideal which is generated by products, let's say L in F XL. And here the condition is that F is not a phase of delta. So here I'm looking at non-phases of delta, and I'm just writing down the monomials corresponding to those non-phases. And this is the Stanley-Wiesner ideal or phase ideal. And okay, so where does this ideal live? It lives inside the polynomial ring on n variables. And here K is just any field right now. So now what is the Stanley-Wiesner ring? So that's now the quotient of this polynomial ring, which I will call S, by this ideal. I just write Stanley-Wiesner. So I won't write Stanley-Wiesner ring again. I just write SR ring. So yeah, okay. So one observation: this Stanley-Wiesner ideal is a square-free monomial ideal. That's the first thing you should note. And the other thing is that if you just want to look at the generators of this ideal, you just have to take the minimal non-phases. So what do I mean by minimal? So maybe let's just look at one of the examples, and there it's easy to see what I mean. So let's say I take the cross polytope again. So delta, so that's the first example. Delta is the cross polytope. I just draw it again like this. Well, let's just take the boundary of the three-dimensional cross polytope. So let's just now, for simplicity, let's number the vertices 1, 2, 3, 4, 5, and 6. So I hope you can see this. So what's I delta? So first of all, I don't have the edge between 1 and 2. So I have x1, x2. Similar, I'm missing the edge from 3 to 5. So I have x3 times x5. And I'm missing the edge from 4 to 6. So I will also get x4 times x6. So now, okay, what else am I missing? For example, I don't have the triangle 1, 2, 3. So I could put, and I just do it, just for a moment, I could put x1, x2, x3 there. But I don't have to put it there, because if I look at the generators, this is already divisible by x1, x2, which is already there. So which means that when I write down the Stanley-Wiesner ideal, I just have to look at the inclusion-wise minimal non-phases. So yeah, let's just say I'm omitting this part again and just take the ideal generated by those three monomials. And you can convince yourself there are no more generators. That's like the minimal set of generators. Okay, let's maybe look at two more examples, which are easy, but which are still somehow nice. So if delta is just is a simplex. So here 2 to the d is just a set of all subsets of the numbers 1 up to d. So what I get here is a d minus 1 dimensional simplex. And in this case, the Stanley-Wiesner ideal is just the polynomial ring, because I don't have any non-phase. I have all possible phases there, so nothing really happens. And maybe the last examples, and I will also put this on this slide, if let's say delta is a boundary of the D simplex. So here I take proper subsets of 1 up to D. Then I'm just missing one face. Then I'm just missing the face consisting of all the vertices. So here, the Stanley-Wissner ideal would be just the ideal generated by the product of all variables. So are there any questions so far? Okay. So, but please feel free to ask. So, yeah. So why do we care?
Martina, maybe next time you can wait some more seconds, because sometimes people are just no.
I can wait. Sorry.
I'm not sure whether there are any questions, but yeah.
Okay, maybe I will just say something. I won't write anything. And if there's any question which comes up, then just ask it. So so now, since I've defined the Stanley-Wissner ring, but now you've got to ask, okay, why do we care? I mean, we have like this combinatorial object, which is somehow, it looks nice. I mean, you can really, yeah, you have some pictures in mind, yeah, there's some geometry and everything. And now I'm defining something algebraic. So why do we care? So let me introduce some more notation to be able to explain this. But maybe let me also just say that there are some algebraic invariants that correspond to combinatorial invariants of the simplicial complex. So you can see some properties of delta in the Stanley-Wissner ring and vice versa. And it's also clear that this is a one correspondence between the Stanley-Wissner ring and the simplicial complex. So when I give you the Stanley-Wissner ideal, you can construct the simplicial complex and vice versa. So somehow both carry the same information, but it turns out that a lot of things are easier to show if you use the Stanley-Wissner ring. And I would like to make this a little bit more precise. So let me define the Hilbert series. So okay, so what's the Hilbert series? I take the dimensions, so K vector space dimensions of the created pieces of my Stanley-Wissner ring. So in here, okay, so what is K delta I? So K delta I are just all polynomials in the Stanley-Wissner ring that are homogeneous. So all monomials appearing have the same degree, and they have degree I. So this is a grading. This defines me a grading on my simplicial complex. And it has a property is that if you multiply something in K delta I with something in K delta J, so of degree J, you get something of degree I plus J. It further has a property that if you look at it as an algebra, it's generated by the degree 1 elements, by the degree 1 part. Yeah. And it's finally generated, which means that if you look at the degree 1 part, there's only a finite number of generators, which is clear in our situation because we only have finite simplicial complexes right now, so we have a finite number of vertices. Okay, so therefore I can define what I wrote down here, and this is called the Hilbert series. So now a good exercise is to show, and I will just write exercise or theorem, but to be honest, it's rather an exercise than a theorem. So what you can show is the following. So H K delta of T equals the following. So it's 1 minus T to the D, where, let's say, what is D? So here I assume delta is of dimension D minus 1. And what do I have in the numerator? I have a sum from I equals 0 to D, f I minus 1 of delta t to the I 1 minus t to the d minus I. So here you already see that you can somehow compute the phase numbers just from the knowledge of the Stanley-Wieser. So now if you look at this numerator here, so this is a polynomial. Let's say this part is a polynomial of degree d. So you get exactly 1 minus t to the d minus 0 if I equals 0. And similar, you get t to the d if I equals 0. So you get something of degree d. And since it's a polynomial of degree d, you can write it in the following way. You can just write it as follows. So write it as so h0 of delta plus h1 of delta t plus, and then there's the last summand, which is h delta of t, hd of delta t to the d. So you just expand this polynomial and you just say, okay, the coefficient in front of t to the I, this coefficient I will call hi of delta. So are there questions so far? No.
Could you repeat what the grading is?
Okay, so you have like, so you mean what this k delta I is? Sorry?
You said before that we have a grading of.
Yeah, so the grading just tells you, okay, so I have, sorry? Okay, so the grading just says, okay, I can decompose my k delta and like pieces, which are of, which I call k delta I. And they have the property that if I multiply something of degree I with something of degree j, I get something of degree I plus j. And this is something which you have for the polynomial ring for sure, and you also have it for the Stanley-Wieser ring. I don't need anything more than this right now. Okay?
Okay. Okay.
Okay, great. Yeah. So now if I have expanded this polynomial, I can define what I call the h vector. So now we say h of delta is just a vector corresponding of those coefficients. So that's the h vector. Okay. I will compute some examples in a minute. Let me just say that, so if you, if you look at this numerator here, you can easily expand the left-hand side. You can just write it down and you will get a formula for hi in terms of fi. And similar, you can do it the other way around. So you can just use some kind of Möbius inversion and then you can just see, okay, if I give you the h vector, then you can also compute the f vector. And to be more precise, the following is true. And again, and this is just some computation, but it's maybe kind of instructive to do it. I will write it as an exercise. So you can show hi of delta is sum j equals 0 to I minus 1 I minus j d minus j I minus j f j minus 1 of delta. And again, the dimension of delta is d minus 1. And the other way around, you can express fi minus 1 of delta as the sum j equals 0 to I d minus j I over I minus choose I minus j hj of delta. So, and the thing which is, okay, so if you look at those formulas, as I said, you can easily compute the formulas just from the Hilbert series and from the definition. So there's not that much to show. But if you look at the formulas and if you think about what I said, so I would like to come up with bounds, so lower bounds and upper bounds for the phase numbers. So now, if one could show bounds for the H vector, then I would also get bounds for the F vector. Just because Fj, any F or any Fi is a non-negative linear combination of the Hj's. So any inequality for H also gives me an inequality for F. And this is something which will be used. So let's maybe do one more example, and then I will make a short break for questions, because then we have the first part. Okay, so examples. So what about the H vector of the D simplex? So anyone from the audience, any idea how this looks like? So if you, so what you could do is you could just plug in, you could either think about, okay, what the Stanley-Wieser ring in this case? So there, in this case, it's just a polynomial ring. And then you write down the Hilbert series for the polynomial ring. And then you see, okay, this is just 1 over 1 minus t to the number of variables. Or you could also plug in to this formula, which is written in the numerator here. And then for the simplex, so what is Fi minus 1? So for the simplex, let's say simplex on D plus 1 vertices, the I-dimensional, I minus 1 dimensional faces are all subsets of cardinality I of the set 1 up to D plus 1. So here, this Fi minus 1 is just D plus 1 choose I. And then you see, okay, just by the binomial theorem, the sum, which is written down here, is really just t plus 1 minus t in parentheses to the d, which is just 1 to the d. It's another way how to see it. So therefore, this is really simple. It's just this vector. And you can play, or you can do something similar for, let's say, the boundary of the D simplex. And if you compute it in this case, you will see it's a little bit more interesting. It's just the all one vector. And now to give you maybe 2 more examples. First of all, our standard example of the cross polytope again. So in this case, you will just get 1, 3, 3, 1, which is also something you can just compute, maybe by the formula. And maybe the last example, just to show you that the H vector is not always that nice, as in the examples. That by that nice, I mean that all entries so far have been non-negative. So if, for example, if you look at this complex, so you have, here you have the vertices. The H vector turns out to be 1, 3, 1, minus 1. So there is a negative entry. So however, there's something I would like to point out. So whenever you have the boundary of a simplicial polytope, or more generally, whenever you have a triangulation of a sphere, in this case, we have the so-called Dehn-Somerville equations, which state the following. They just say, okay, Hi equals Hd minus I. And this is something you also see in the example. So for example, for the boundary of the simplex, we just have the all one vector. So for sure, this is symmetric. for the cross polytope, this hi equals hd minus I just says, okay, the first entry equals the last entry, the second entry equals the second last entry, and so on. And I'm not going to show this, but I will use this later. This is why I would like to point it out. And I guess now is a good point to pause. Okay, then let's just go on. So what would I like to do in the next part? So first of all, I would like to introduce full Macaulay complexes. And here it gets a little bit more algebraic, but that's nothing really, let's say nothing really serious or really difficult. So let's just start with a definition. Let's say we have delta a d minus 1 dimensional simplicial complex. I just write SC a little bit shorter. And then we say, okay, elements theta 1 up to theta d, which lie in the Stanley-Wiesner ring and which have degree 1. So they are linear forms. They are called a linear system of parameters. For the Stanley-Wiesner ring, if the following two conditions hold. Though the first condition is that I want those elements to be algebraically independent. Over the field K. Okay, so what does this mean? This means that if you take any polynomial which has coefficients in K and has D variables, and if you plug in your forms theta 1 up to theta d, then this should always be non-zero. That's the first condition. The second condition I would like to have is that K delta is finally generated as a module over the polynomial ring in theta 1 up to theta d. So what do I mean by this? I just mean that I can write K delta as a sum of some eta I, which are homogeneous elements. And then I have the polynomial ring in the form theta 1 up to theta d. So here, the theta I are homogeneous elements. So what does this mean intuitively? So basically, this somehow means that your Stanley-Wiesner ring somehow behaves like a polynomial ring. At least a good chunk of it behaves like a polynomial ring. But there might be dependencies between these eta I. This is somehow how you should think about this. I will make an example in a minute. So another way how to write this is, how to define this, and this is maybe easier to imagine, is that the dimension of the Stanley-Wiesner ring, where you mod out by those forms, and I will just write them as theta, and then I take the ideal generated by the theta. This dimension should be finite. That's another way how to write this condition, and this condition is somehow easier to handle, I guess. No matter, we will need also the other condition. This is why I wrote it down. Okay, so first of all, you could ask, okay, that's a definition, but do those things exist?
Martina?
Yes.
There was a question.
Capital theta?
Yeah. What's the question?
What is capital theta again?
Capital theta is just the set of those elements, theta 1 up to theta d. I added it in the definition at the very beginning, in the second line.
Okay, thanks. I missed it.
No problem. Okay. And okay, instead of writing linear system of parameters the whole time, I will just write LSOP for short. Okay, so as I said, you could ask, okay, do those sets exist? Do those systems exist? Yes, they do if the field is infinite. So I will now always assume that the field is infinite. And this is just due to Noether normalization, which exactly says that something like this has to exist. That's also why I won't write down Noether normalization right now. Just what is important right now, we can always find such a system whenever we have an infinite field. So let's look at an example. Or maybe two examples, I guess. So the first example is the following. So let's say the simplicial complex is a very easy one. It just consists of two edges, 1, 2, 3. Ah. Okay, so what's the Stanley-Wiesner ring? So this is my delta. What's the Stanley-Wiesner ring? It's a polynomial ring in 3 variables, x1, x2, x3, where I mod out the ideal generated by x1 times x3. So now claim x1, x2 is not an LSOP in this case. However, x1 plus x2, x2 plus x3 is an LSOP. And I will maybe just explain why those element x1 plus x2, x2 plus x3 are an LSOP. So for this, let's just write down what is k delta modulo those two forms. So what do I mod out? So first of all, when I mod out x1 plus x2, I basically identify x1 and x2. Similar, if I mod out x2 plus x3, I identify x2 and x3. So in total, I have identified all my variables, which means I'm just left with one variable. Let's just say that's x1. But then I have modded out x1 times x3, which now corresponds to the square of x1. So as a k vector space, this is just isomorphic to the span of 1 and x1. Nothing else. I've modded out everything else. So in particular, as a k vector space, this is finite. And that was the second condition I wrote down. So this is an LSOP. When you do the same for the other system, for this x1, x2, what you will see is that you are left with something which is, so what do? You mod out two variables, so x1, x3. But now you also, so then you have everything which is polynomial in x3. This is left. So what is really left inside then is 1, x3, x3 squared, and all the powers of x3. And this is by far not finite. And this is why x1, x2 won't give you an LSOP. Okay. Yeah. So now when do we call a simplicial complex Cohn-Macaulay? So delta is Cohn-Macaulay
Martina,
over K. Yes.
there's a question.
Yes.
By Marielle.
Mm-hmm.
So the LSOP looks like it comes from the edges. Does this generalize or is it a coincidence?
Okay, so it does not really come from the edges, but there is a nice criterion. So it's called the Kind-Kleinschmidt criterion, which basically states the following. If you, a set of, let's say, D linear forms is a linear system of parameters. Let's say you take any phase. Let's say just take a maximal dimensional phase of your simplicial complex. And then take your D linear forms and restrict to the variables corresponding to this phase. so that correspond to the vertices of this space. And then you get, again, you get bilinear forms. And if those span a vector space of whose dimension is exactly the cardinality of the face you have taken, if this is true for any face, then you have an LSOP. So for example, if you look at, okay, let's say in this example, we restrict to the edge 1, 2. Then this x1 would just give me, the first form would give me x1 plus x2. The second form would give me x2. Well, this is something of dimension 2. This is fine. So now if I restrict to the second edge, I would get an x2 from the first form, and I would get x2 plus x3 from the second form. So again, something of dimension 2, that's fine. However, if you do it with this x1, x2, which we had, and if you restrict it to the edge 2, 3, you just get x2. So this is one dimensional, but it should be two dimensional. So this is, yeah, there is a nice way how to see this. Okay.
So does this work on like the linear system of parameters where you take sums of the vertices, like without coefficients, without, I mean, are you taking, in this case, we're taking x1 plus x2 and x2 plus x3. If
Coefficients
you had like
don't matter.
Coefficients don't matter, okay. Nice, and what's the name of the criterion again?
Kind-Kleinschmidt, I can write it down.
Okay, yes, thanks.
And if you want, I can add it to the handwritten notes. Okay.
It's fine.
Okay, now let's come back to the definition of Cohn-Macaulay complexes. So when is delta Cohn-Macaulay? So first of all, it should be Cohn-Macaulay over K if K delta is a free module over K theta 1 up to theta d. For some, and then it's actually every LSOP. So, okay, so we have already seen from the definition of the linear system of parameter that K delta is a module over the polynomial ring in theta 1 up to theta d. So what does free now mean? So this free here just means that if you take any element in K delta, there is a unique way of writing it in the form we had. So let's say there exists those homogeneous elements we had before, eta 1 up to eta s, so that any A in K delta can be uniquely written as some where we have those eta I, and then you have some element of the polynomial ring whose variables are those theta 1 up to theta d. So it's some polynomial pi in the variable theta 1 up to theta d. And whenever you can do this uniquely, you are in the Cohn-Macaulay case. So I guess I should do examples. So first example, very easy example. Let's just take 2 points. So in this case, what's the Stanley-Wiesner ring? So K delta is just the polynomial ring x1, x2 divided out by the Stanley-Wiesner idea, which is generated by x1 times x2. So now, okay, so how many elements should an LSOP have here? So it should have just one element because we are in dimension 0 and we always have one element more. So we need to take one element, and I claim that if you just take x1 plus x2, this is an LSOP. And now, okay, since I already said what is this Klein-Schmidt criterion, you can also use this now to check this is really an LSOP. So if you restrict to the vertex 1, you're left with x1. If you restrict to the vertex 2, you're left with x2. Both is of dimension 1, so you're fine. So nothing bad can happen in this case. So now K delta is free over K x1 plus x2. So why? So first of all, so you can, if you look at, let's say, this part here, wait, no, this is not what I want to write, to be honest. Yeah, so let's say, just say, you can set eta 1 to 1 and you can set eta 2 to x1. So if you do it this way, then you have x1 to the p can be written as x1 times x1 plus x2 times p minus 1. So here you have your eta 1, then this x1 plus x2 to the power of p minus 1 lies inside this polynomial ring with where you have the x1 plus x2 as a variable. And then similar, you can write x to the p as 1 times x1 plus x2 to the p minus x1 plus x2 to the p minus 1. Yes. So here, if you compute it, all terms of the form x1 to some power times x2 to some power will vanish again, because x1, x2 lies in the Stanley-Wiesner ideal. So from the first part, you just get x1 to the p plus x2 to the p. From the last part, you just get x1 to the p. So this is really x2 to the p. And one can show this is unique. So those expressions are unique. There's no other way of writing this. Okay. Okay, and then we say, okay, such an LSOP is called regular. So whenever we have this, we say that we have a regular LSOP. Okay, so what this also means is that this complex, so the complex consisting of two vertices, is Cohn-Macaulay. So we also have delta is. I just write CM. So over our field K. Are there any questions so far?
I have a question. How would you go about showing that the expansions are unique?
That's the tricky part, which I omitted.
Okay.
You would basically try to assume that there's another expression, and would try to get to some contradiction at some point. But
so there's no like nice way.
No.
Okay.
I mean, there's a nicer way to see if something is Cohn-Macaulay, which is the Reasoner criterion, which I won't mention just for time reasons. So there's like a topological way how you can see it from your simplicial complex. Yeah, but maybe if you want, we can speak about this in one of the coffee breaks. I can say more. Okay. Okay, now as an example, or as an exercise, not example, exercise, let's say, show that the following complex is not Cohn-Macaulay. So just take an edge and an isolated vertex. Okay. So what you need to do is you need to take some LSOP and you need to show that this is not regular. So that you can express something in a non-unique way. That's what you need to show. Okay. So now you could ask, okay, why do we care for Cohn-Macaulay complexes? And there's a nice feature of those complexes. They are really nice if you want to say something about the H vector. So what is easy to show is the following. So one can show, and this is basically just a counting argument, that HI is just the dimension of K delta, where you mod out a linear system of parameters and you take the degree I part. So assuming that delta is Cohn-Macaulay. So in other words, what this says is that if you look at the Hilbert series of this quotient, then this is just I equals 0 to D, HI T to the I. So what you also see from this is that the Hilbert series does not depend on the linear system of parameters you have chosen. And this is just because this linear system of parameters is something which we call a regular sequence. And whenever you mod out by such a regular sequence, the Hilbert series will just be, you just multiply it with 1 minus t for each element. This is why we are just left with a numerator polynomial of the Hilbert series of K delta. Okay. So in particular, if delta is Cohn-Macaulay, we also have that HI of delta is non-negative. And this is, in particular, this is a lower bound for HI. So that's also a lower bound for the F vector. So here we have our first lower bound, non-trivial lower bound. And we also have another criterion to check if something is not Cohn-Macaulay. So for example, if you look at this complex I've written up here, for which you should show that it's non-Cohn-Macaulay, and you should just show it from the definition, you can compute the H vector to be 1, 1, minus 1. So this also says that this cannot be Cohn-Macaulay because of this minus 1. And this is now easy to check. Okay, so I guess I have like 20 more minutes, Lorenzo? Okay, great. Because then I will come to the last part. So I should say something concerning symmetry. But first of all, are there questions?
Yes, I have a question. So I knew that, or there was this definition of Cohen-Macaulay rings that uses an homogeneous systems of parameters instead of a linear one. And I was asking myself why in this case do we only consider linear terms and of not bigger degree?
Okay, so so you can define homogeneous system of parameters, which is just used, you don't require linear. But if you want to say something about the Hilbert series, then modding out by something linear, enables you to say something. And because you just know, okay, if you mod out by a regular linear element, then I just multiply the Hilbert series by 1 minus t, which is really, really easy. And this is one reason. Okay, further questions?
Is there any algebraic interpretation of the H star or the H coefficients if it's not Cohen-Macaulay, like for other classes of simplicial complexes?
Yeah, so there, you mean algebraic interpretation?
Or
okay,
any
so
kind of interpretation.
Okay, so, yeah. Okay, so if you ask for an algebraic interpretation, so if it's not Cohn-Macaulay, then you could, for example, take something which is called Buchsbaum, which is a weaker property, let's just say. And then you can still say something about the H vector, but then you are, okay, so somehow you have to take into account not only the usual H vector, but also the topology of the space. I know that this is a very, very vague answer, but if I would say more, then then we would need a lot of more time, much more time.
Thank you.
But you can generalize this in a nice way, let's say. Yeah, more questions. Okay. Then let's finally come to symmetries. Let's see how far we can go. So, I mean, if we don't manage to do everything, it's no problem. Because also Uwe's stuff is completely independent from my stuff. So I can pause everywhere. So let's just try. So third part, lower bound theorems for simplicial complexes with symmetry. And I will call the symmetry I need P symmetry. And P usually is a prime. Okay. So first the definition. So let's say we have a group G. And we say, okay, this group acts on our simplicial complex delta if we have a group homomorphism, if there exists group homomorphism from G into the automorphism group of delta. So what's the automorphism group? Let's just write this down. So you just have bijections from delta itself. And you want that whenever F is contained in G, this should also be true for the images. So that's the automorphism group. So what you do is to any group element, you associate an automorphism of delta. And okay, so this is something which maybe right now looks a little bit weird, but we will see a lot of examples in a minute. So okay, mostly I will be interested in fixed point free such actions. So what do I mean by fixed point free? Just what you think it is. You just say, okay, for every element G and every F and delta, when you have that the automorphism determined by G applied to your face F, if this gives you your face F, then either G should be the unit element of the group or F should be the empty face. Okay. We either have F is the empty set or G is the unit of the group. And I will usually write it as a multiplicative group, so which is why I write 1G. Okay, so some kind of notation here. So I don't want to bother to write P of G. So I will just write G applied to F directly. So here a notation. Whenever I write something like this, G of F, I mean P of G applied to F. Okay, this is the first thing. Okay, so and when we have a group acting on delta and the group has P elements, and if we further have this action is fixed point free, then we say delta has a P symmetry. Okay, so here delta has a fixed point free P symmetry. Whenever we have such an action. Okay, and I guess, okay, and here I should also say, or write down, here G should have P elements. Okay, so I won't say usually now that everything is fixed point free. I will just assume it. But maybe let's now look at some examples. So because you could ask, okay, what are now examples? Are there many, or are there just a few? And there are a lot of examples. So we have already seen one example. So if we take delta, again, the boundary of the cross polytope. And now I take the d-dimensional cross polytope. So which is nothing else but the boundary of the convex hull of the unit vectors. In this case, we have a two symmetry where, okay, so what's the group? The group is C2. So I have just C2. Let's say I have G and I have the unit element. So G squared is a unit again. And now what's the action? Okay, so the identity does nothing. So there I have just the identity itself. And what does the second element do? It just maps x to minus x. So in particular, it maps I to minus EI. So here we have G of, let's say, EJ or plus minus EJ. What does it do? It just maps it to minus plus EJ. And that's the action. And this describes an action on the faces, where you just apply it to every element of the vertex, to every vertex of the face. Yeah. So what do we have in this situation? So in this situation, this action is nothing else than an involution on the vertex set. Because if we apply G twice, we just get the identity back. And whenever we have something like this, then we say that is centrally symmetric. So it's okay. So okay, let's maybe write this. So the action of C2 is given by an involution, or by a free involution to be precise, because we don't have any fixed points. So let's call this involution alpha, just to have a name for this map right now. So what do I mean by free involution? I mean, whenever I don't take the empty set, I should get again a phase of delta. Well, this is nothing really. Yeah, this is something you should assume so that everything makes sense. You also want, in this case, not to have any fixed points except the empty set again. And the other thing is, it's an involution. So if you apply it twice, you get the identity. So this is just F. And whenever we are in this situation, we call those complexes centrally symmetric. Okay, so those simplicial complexes are called centrally symmetric. Okay. Questions so far?
Yeah, so I didn't get exactly what is an automorphism of a simplicial complex. So you said it is a bijection on the ground set to itself.
It's not a bijection on the ground set. It's a bijection. Okay, it's also a bijection on the ground set, but that's not enough. It's a bijection on the simplicial complex, so on the faces. So if you apply, I mean, if you take the collection of faces of delta, and now you take the collection where you have applied this the automorphism to any face, you get the same set.
I see. Okay. So, but yeah, so but if I want to describe it as just as a bijection on the ground set, then I should somehow require that any face stays a face, right?
Any face stays a face, and for every face has a pre-image, because otherwise it can't be in bijection. But you're right in the way that you can describe any automorphism by just prescribing it on the vertices. So if you know what's happening on the vertices, you know what's happening with the faces.
Thanks.
Okay. Further questions?
So could you tell us what the automorphism? Oh, sorry. What would the automorphism of a group of the set of the cross polytope be?
Okay, so for example, you would just get where you map EI to minus EI, those things. And where you, I mean, you could, for example, you could fix, let's take the three-dimensional cross polytope. So you could fix this equator, and you could just switch the vertices on top and on the bottom. So you map E1 to minus E1. But this wouldn't be a fixed point free automorphism. So if you think about something which is fixed point free, you should switch E1 and minus E1, and you should also switch E2 and minus E2 and E3 and minus E3. And if this is everything, fixed point free, I guess fixed point free, there's nothing else in this case. If you allow fixed point there, you have like the combinations of just switching pairs. Okay. Further questions?
Okay.
I have a question again about the definition of the automorphism group. You had an implication there. Is that sometimes not an equivalence?
It is an equivalence.
Okay. Yeah.
Okay. More. Okay. Okay. So then let's look at, I guess I have time at least for one more example. And then I will talk about bounds tomorrow, but that's completely fine. Okay, so second example. Let's say this is example 1. Now example 2. So if we speak about polytopes, then I would like to have something which I call a linear P symmetry. So in the literature, it's often just called P symmetry. But yeah, here I just really want to call it this way. So this is something you can really imagine. So you have a polytope P, and then this is nothing else than a fixed point free linear invertible linear transformation. Which I call alpha of R to the n, which has the following property. If you, the image of P under this transformation is a polytope itself. And why P symmetry? Because it has order P as an element of the symmetric group. As an element of the symmetric group. So this alpha determines a permutation on the vertices of P. And as such a permutation, if it's of order P, so if you apply it P times, then you just get the identity, then we call it linear P symmetry. And linear just refers to the fact, okay, you have a linear transformation. So what does fixed point free mean? I mean, there is one obvious fixed point which you always have, which is the origin, because of the linear transformation. But except for the origin, there's no other fixed point. That's what I mean by fixed point free. And in particular, we have seen one of those examples already, namely for the centrally symmetric case, where this alpha just mapped x to minus x. Okay. Yeah, so I guess I don't have, do I have time or don't I?
According to my clock, you have 2 minutes.
2 minutes. Okay, so then I guess I won't go on right now. I will just say what I'm gonna do tomorrow. So I guess tomorrow I will start with another big class of p-symmetric polytopes, which are called p-symmetrically stacked polytopes. And yeah, this is just a huge class, and it's an infinite class in particular, which we will define. Then I will speak a little bit about lower bounds for those. I will speak about lower bounds for Cohen-Macaulay complexes. And I might speak a little bit about upper bounds. And yeah, I have probably more in the notes, but that, as I said, that doesn't really matter. So to be honest, I'm glad that you ask questions, and I prefer to not cover too much stuff than to cover everything and nobody's asking anything. Yeah, so thanks for listening.
Thank you, Martina. I will pause, actually stop the video now so we can ask questions.